Hi everyone, I hope you're all doing fine. My name is Fabian Böhm and I am joined by my co-author Ludwig Englbrecht to present our paper Designing a Decision Support Visualization for Digital Life Forensic Investigations. Let's take a quick look on the outline of our talk. I will start with a brief introduction, bring up the addressed research questions, and briefly show the methodology. Then Ludwig takes over to define the problem of decision support for life forensics more in depth. I will walk afterwards through the application of the methodology to come up with a design for the visual decision support solution to help forensic investigators. And finally, Ludwig will demonstrate a possible application of this proposed design and conclude our work. As we start, let's first consider this happy device with the same memory, nicely working volumes, and everything else looking pretty good for this device. Maybe now a malware might corrupt one of the volumes of this device, and a forensic expert here on the left side of the slide might become aware, or at least suspicious, of a possible problem on our not so happy device now. So what a forensic investigator traditionally does now is he turns off the device, he shuts it down and follows some steps for a forensic analysis to understand what happened on the device and collect evidence of the malware being there on the volumes of this device. However, a fileless malware does not reside on the computer's or device's volumes, but in its memory. So what happens if a forensic investigator turns off the device? Well, it's a bit oversimplified, but basically the memory is lost and there's little to no evidence left on the turned off computer of the malware. So the forensic investigator can't analyze the fileless malware properly. Therefore, it is necessary to keep the device under investigation running while at the same time being able to perform a forensic investigation on this device. That's why we need live digital forensic investigations. During such a live digital forensic investigation, analysts need to make fast and well-informed decisions as the data on the running device is constantly changing. They have numerous analysis tools at hand to do so. However, a poor choice of tools to deploy to analyze the device could compromise or even destroy important artifacts and evidence. Thus, fast and careful decisions about the forensic tools to carry out the analysis have to be made. And to help forensic experts making well-informed decisions, we propose a visual decision support system. This leads us to three main research questions which we address in this work. First, we need to understand better where, in terms of process steps, forensic investigators need decision support. Then we need to break this down to their actual tasks and the relevant data. And finally, we have to answer the questions how an actual visual decision support systems for these analyses can be designed. Our work mainly follows the nested blocks and guidelines methodology to ensure the reproducibility of a visual design. This methodology consists of four main layers, where each layer is instantiated by more fine granular building blocks and relationships, so-called guidelines between those building blocks. So this is an overview of the methodology, which can get quite complex. We have this domain problem characterization, which aims to build an understanding of the problem for which a visualization should be designed. The data and operation abstraction design analyzes the data and the user tasks stemming from the domain problem from a visualization point of view. And the encoding and interaction technique design decides which visualization techniques, as bar charts, line charts, etc., are best suited for the data and user tasks at hand, and which interactions with the visualizations are necessary. The algorithm design now just is the actual implementation of these encodings and interactions, and is something we did not go into yet, as it is part of our currently ongoing work.
Thank you, Fabian, for the great introduction and the motivation for our approach. My name is Ludwig, and I will continue with the linkage between live digital forensics and visual security analytics. So, the collection analysis of digital evidence should be based on a defined comprehensive process model. We used the common definition of a forensic investigation presented by Kent et al. And extended this approach with visual decision support. Let's have a look at the process here. One stage is the collection. During the collection, data related to the criminal activity are identified, labeled, recorded, and secured from all potential sources. By applying visual security analytics, we can also identify additional sources that needs to be secured. At the examination phase of the process, the data previously collected by the step collection is evaluated. The aim is to identify and extract relevant data for the investigation. Since our approach is applied to a live investigation, a visual analysis of the data allows the decision to include additional data sources for the analysis. Consequently, the visual decision support creates a loop back to the previous stage, but we made the decision to include more data sources into the investigation. At the analysis stage of the process, so the data is analyzed in depth and interpreted to establish connections between persons, places, objects, and events. Also to obtain useful information regarding specific question of the law. Findings from the visual analysis are directly incorporated into the analysis process. At the reporting stage, the results of the analysis are prepared and presented, also including some procedures and decisions that have been made during the investigation process. Also, the visual representation can contribute to the understanding of the incident. By having the previously described task of the investigation process in mind, we have selected common tasks of the domain experts during a live forensic investigation. These are very specific since the investigator needs to collect and analyze near real-time forensic data. First, data acquisition. Investigators need to decide what data they export from a device. Second, they need to establish intelligence. Please consider here no analysis of the actual crime is carried out, but rather the region of possible purposeful evidence is identified. Within a live forensic investigation, they need to decide what further areas they want to include for the investigation. Since it's a live forensic investigation, we need to have a look at the memory and data analysis. Previously identified data is examined for suspicious features and are put into context to reconstruct the course of events. Very important is to ensure the chain of custody during the investigation. The documentation can be assisted by documenting every step of the live forensic investigation, and they can be used for the final report. To provide decision support during a live forensic investigation, it is important to consider the right type of data. We use the 19 categories of the Artifact Genome Project as a baseline for our approach. These 19 categories are selected observables from the MITRE Cybox. They use them for a prominent and common cyber observable exchange. But not all 19 categories can be used for our approach. We selected the following 6 categories of the HGP project as potential candidates for digital evidence that is available during a live digital forensic investigation. It is important for us that these data can be acquired without major interference due to the installation and execution of additional applications. By analyzing the previously described data, Visual Security Analytics allows experts to make better context-based decisions about the tools to apply for further investigation.
We now step into designing a visualization for supporting the forensic investigator, and therefore start to fill the layers of the nested blocks and guidelines methodology. One of the most important paradigms of visualization design is to keep the user's task always in mind and to analyze how you can fulfill this task with the data at hand. And keep in mind that this first step of the methodology, this first layer, is defined to use the vocabulary of the domain, so of the forensic analysis domain in our case here. So this means that we can just describe our problem from a forensic point of view in this first layer, and up to now we did not need to bother with any visualization terminology. And therefore the problem domain characterization can be derived from the previous slide, so from the content Ludwig just presented to you. On these slides, we have seen already that there are 4 essential high-level tasks for forensic investigators during a live digital forensic analysis. And we also identified 4 types of very volatile data which should be analyzed or which should be displayed on a visual decision support solution. And analysts need a way for lateral visual movement in this data, enabling them to browse through the data and identify artifacts that need further investigation with specific forensic analysis methods. So this summarizes the contribution from the previous slides and allows us to move into designing a visualization for this specific problem. The next step towards visualization is the abstraction of the domain problems and also of the domain data to move more into the direction of visualization terminology. This means we are now translating the tasks and the data descriptions from a forensic vocabulary and perspective to a more visualization perspective. We need to understand what the tasks of the forensic investigators mean from a visualization point of view. For the tasks, we follow a common typology taxonomy, which defines visualization tasks from the why point of view, meaning why is a forensic investigator using a visual representation. From the domain problem, we can derive mainly 3 drivers why forensic investigators are using or are needing visualization. They consume, they search, and also they query. So these very high-level tasks from the task taxonomy can be broken down into more fine granular tasks. For example, the consume is at the highest level. A forensic investigator uses the visualization for consuming the data, or more specifically to discover interesting patterns or points or outliers in the data. So this can be afterwards specified as a search task. So the investigator explores, browses, or locates, depending on whether the target of the investigation and its location in the data is known or not. And for a successful search, therefore, it is necessary to be able to carry out queries, therefore comparing data and identifying relevant data. Looking at the volatile domain data from a visualization point of view, we identify mainly 3 different types of multi-dimensional data that we have to deal with in our visualization design. Mostly it's time series data, like system statistics, or categorical data, maybe different types of logs, and also network data, like the network packages a device is sending and receiving. As we now understand the visual tasks and data, we can set to define encodings and interactions, allowing the forensic investigators to perform these tasks on the data at hand. The last step, the selection of visual encoding, so the actual visualization types, is a pretty subjective step. But with the nested blocks and guidelines model, this step at least gets comprehensible and the thought process behind it becomes more clear. So we now take the results of the data and operation abstraction to derive encodings and interactions, and the a bit simplified results can be seen on the slide. We basically identify 6 different encodings with mainly 4 different interactions that should be allowed on their respective visualization types, but also across them. In the full-blown nested blocks and guidelines model, we would have connected the different operations and data abstractions with each encoding and interaction they are related to, but this basically leads, at least for a slide here, to an unreadable model, which is why we simplified it a little bit here. So now let's take a look at the final visualization design. So this is the proposed visualization design, which we derive from this methodology. It comprises of 5 main parts. On the very top, we have this investigation timeline, which should allow the selection of a time window where all other visualizations only then display the data for this respective time window. The timeline also allows the annotation in terms of marking points of interest to come back later. So this is this orange A marker on the timeline. So a forensic analyst probably already saw something interesting happening in this time where this A marker is set on the timeline. The network activity on the top left displays the communication of different processes, identifiable through their process IDs, with other IPs. The IPs are clustered based on the IP ranges and colors of the edges between the processes, and the IPs encode the intensity of the connection in terms of number of connections, but also the amount of data sent through this connection. The system activity on the bottom left reports on logs, so several log types can be selected from the checkboxes, and spikes, for example, for error messages become very apparent in this encoding. We have the read-write entropy on the top right corner, which displays the entropy, so a value between 0 and 1 of read and write actions on different drives, also selectable through the checkboxes. This is, for example, very useful for detecting when a lot of encrypted data is written on a drive. And finally, we have the system performance on the bottom right corner of the design, which shows the overall CPU and memory performance of the system, but also with this smaller sparkline graphs on the bottom half of this system performance display, the CPU and memory usage of different processes. This view overall should be implemented as a coordinated view where interactions on one visualization also influence the display on the other visualizations. For example, selecting a time frame, as I already said, or clicking a process on the system performance highlights probably this process in the network activity and the connections of this specific process. And now Ludwig goes through a simple, small use cases where we can see the benefits of these specific encoding techniques in more detail.
Thank you, Fabian, for presenting the methodology and the final visualization design of our approach. Now we go over to a simple use case. We decided to choose Poweliks since it's a well-known and good documented fileless malware attack. It attacks Windows-based systems, and in 2014, it moved from a file-based to a fileless variant. Infected PCs became part of a click fraud botnet. This specific fileless malware acts without leaving an actual file on the computer's file system. All data is stored in the registry and memory by injecting code into legitimate processes. Therefore, it's hard to detect once again a foothold on the system. Also, restarting the affected device does not remove it as it reboots itself from altered registry entries. This makes it a very dangerous and advanced type of fileless malware. Now let's have a look how Poweliks injects its malicious code into an affected system. It starts with registry entries. So we have one entry called default. This entry contains a command for loading and decrypting another value. The decrypted value contains a PowerShell script. The PowerShell script decrypts Watchdog DLL, which is a legitimate software for Windows, and Watchdog DLL is loaded and injects malicious code into legitimate process instances. Now we apply our approach on an affected system by analyzing the network activity. First, Poweliks prepares the infected system for further actions. It checks if PowerShell and all needed .NET frameworks are present. If not, they are downloaded from the official Microsoft website and installed. On the figure at the right-hand side, we can see this with a communication to Microsoft. Also, the infected PC can talk to a command and control server. There we can see some short requests and responses with small payloads. We can also observe a frequent connection to these IP addresses. But what is more important is the ad-clicking component of Poweliks. We can see many different IP addresses that are requested, and all these connections originate from a single process. This is also indicated at the right-hand side. By analyzing the read-write entropy, we can get an abstract view on the process data on the system. Since the malware requests up to 3,000 ads per day on a single computer, a lot of temporary internet files are created and processed. These can be observed without knowing what is exactly in the file by looking at the entropy. This is indicated at the right-hand side. It is also very likely that the malware also clicks another bad malware and gets in contact with some ransomware. This is not very good, but we can observe also this if a ransomware starts to decrypt files on the system. Now we analyze the system activity. Poweliks uses Watchdog and PowerShell scripts. This is very powerful in combination. But they tried to lower the browser security settings for the necessary ad-clicking behavior. These settings that are changed generates a lot of event logs like warnings or error logs, and this can be observed by increasing value of some warnings or error logs. Let's have a look at the picture at the right-hand side. We can see an increasing amount of warnings. The domain experts can see these increasing values and decide what is the next right direction in the investigation. Here, the investigator can decide, based on the previously acquired information, to have a deeper look into the registry and hopefully find Poweliks. Oh, but wait, we have also to analyze the system performance. Poweliks does not significantly affect the performance of the infected system because it would like to perform its ad-clicking performance in the background and don't want to get the attention of the user. For this, CPU and RAM are used as you usually visit a website. But RAM and CPU can indicate possible directions of the investigation. Because Poweliks hides different legitimate and common processes, it can be indicated that they need a lot more CPU or RAM, as it's common for this type of application. This provides also further details and information for the investigation. Now let's conclude our work. First, we showed that we can utilize Visual Security Analytics as a decision support for a live digital forensic investigation. We showed the application of a methodology derived from the visualization domain. After that, we showcased how Visual Security Analytics can help to solve problems of a live digital forensic investigation. Our future work will be to identify a classification scheme for Fileless Malware based on typical behavior. We also plan to design a visualization for various behavior types and present a more generalization of a modular design for various types of Fileless malware. Thank you very much for your attention. We hope you have enjoyed our presentation. We are happy to answer your question at the virtual conference, and also feedback is very welcome. See you there.